Springs. Here we have a spring of length L. If we apply a force, the spring will extend by a length delta L. Plotting a graph of force against extension, we get a straight line through the origin. This shows us that force is directly proportional to extension. This is known as Hooke's law. We can write this as F alpha, meaning is directly proportional to the extension. Adding a constant of proportionality, we can write F is equal to K delta L. The spring constant K is then given by the force over the extension for a particular spring. The stiffer the spring, the greater the spring constant will be, as a greater force will be needed to provide a particular extension. The units of the spring constant K are newtons per metre. Let's look at an example. An archer exerts a force of 250 newtons to pull the string of a bow back by 40 centimetres. Calculate the spring constant for the bow. Well, spring constant K is given by force divided by extension. The force is 250 newtons, the extension 40 centimetres or 0.40 metres, giving a spring constant of 625 newtons per metre. A spring doesn't continue to obey Hooke's law regardless of the force applied. If we apply a larger and larger force, eventually the spring will go away from Hooke's law like this. If we now remove the load from the spring, it would follow a line back something like this, and there is now a permanent extension. The spring has been damaged by the excessive force. This point here, at which the spring goes away from Hooke's law, is known as the elastic limit. Beyond this point, the spring is no longer elastic and will no longer return to its original length. Here we have two springs joined end to end, supporting a load W. We say the springs are in series. Both springs are subjected to the load W, and so we can find the extension of A as the load W divided by the spring constant for A. Likewise, the extension for B will be given by the load W divided by the spring constant for B. The total extension is simply the sum of the extension of A and the extension of B, which is what we have here. If we consider the two springs as one system, then we can say that the total extension will be given by the load W over the spring constant for the two springs, or the total spring constant. And if we divide throughout by W, we get that 1 over the spring constant for the system is equal to 1 over the spring constant for A plus 1 over the spring constant for B. Here we have two springs side by side. Both springs support the weight and both extend by the same amount. We say that the springs are in parallel. So the weight down, W, will be equal to the sum of the forces up, given by the spring constant of A multiplied by the extension, plus the spring constant of B multiplied by the extension. Or we can say that the weight W is equal to the spring constant of the system, or the spring constant total, multiplied by the extension. So, dividing throughout by delta L, we get this term showing that the total spring constant of the system is simply equal to the sum of the individual spring constants of the springs in parallel. The energy stored in a spring. Here again we have our spring of length L. We apply a force and extend it by a length delta L. Again, plotting a graph of force against extension, we would get the straight line through the origin. Now, force multiplied by a distance is equal to work done. So if we find the area under the graph here, which is half force times extension, This will give us the energy stored in the spring. So we can write that the energy in a spring is half force times extension. Note the energy isn't the total final force multiplied by extension, as the force actually increases as the spring extends.